Okay, so last time we started to discuss some kind of the slightly kind of different way in terms of like making the genetic models inspired by the Langevin dynamics and also the way to basically calculate these coordinate functions. And the basic idea here was that like what if we basically assume that we are basically having some kind of large scale training data and just like making our regeneration process is not really generation, but just like picking one of the data point in the given the training the data set. So that's kind of really the possible way, but the things that we wanted to have in terms of the feature in our digital model is to make some kind of the making some kind of the novel images, not just like picking one of those kind of images. So here the question is how can we basically generate some kind of the new data points that are basically not identical to any of the specific the data points. So for that, the basic idea that we started to see last time is to add some sort of the blurriness into the training data. So basically what we can see is that, let's say this like QXO here is kind of the underlying the distribution for the data points that we have. So that's the kind of the information that we don't know, right? We only have the samples from the QXO. So it means that if we really want to directly sample the data points from the QXO, that will be really just like just picking one of the existing the training the data points. So that's not what we want to do because we want to make some kind of the something new, the data point. So for that, basically we are basically adding some kind of the Gaussian noise in terms like making some like Gaussian smoothed the version of the distribution like this. So you can see that the new distribution becomes like something that is like applying some sort of the Gaussian convolution into the some underlying the distribution here, the QX0. So we are basically defining some kind of the new data distribution, which becomes the QXT. So by adding some kind of the Gaussian noise into the underlying the distribution, we want to basically sample from this and making something that is close to the one of the training the data points, but still it's kind of new. So that's basically what we want to do. So the question for now is that then how we can sample from this kind of the new the data distribution, the QXT, right? So for that, the basic idea was to leverage the idea of the Langevin dynamics, which was basically very the good idea in terms of that we don't need to directly have the information of the QXT. We just need to have some of the information of the score function. So once we can compute the score, which is the gradient of the log the probability, and based on that, we can basically sample from that the distribution by iterating this kind of process, right? Starting from the sample of any of the prior distribution, and then basically moving that point using this kind of the step, using this core function here. Okay. So this is already actually quite close with like what we are doing in our in the DDPM process, right? So we are going to we are basically seeing some kind of the similarity between the DDPM and this process. Then this means is that for the new data distribution, for the QXT, this distribution, the only thing that we need to know is basically this core information, right? This gradient of the log the probability. So then the question is basically how we can compute this core function for the Gaussian, the blurred, the distributions. And for that, the basic idea also was that we are going to train the score prediction the network like this by minimizing the L2 loss with the score function here. And it turns out to be that if you derive all the things into the new expected value here, then we can actually see that this score function can be seen as kind of the expected value over those things, basically sampling the XU and then sampling the XT based on that. Then basically this expected value becomes actually matching the score function for the conditional distribution. So that's basically the basic idea in terms of that. We are going to train this score function in a way that we can perform the Langevin dynamics, while this score function, score the predictor, is trained to basically match the score function for the conditional distribution, while basically computing this expected value. Then it becomes basically more feasible because now for this conditional distribution, this is basically what we defined as the Gaussian distribution, right? for the Gaussian distribution, we know how we can compute the score function, right? It's just like simply just taking the gradient of the log of the probability. So and then now we can see that, training this like score, the predictor becomes feasible because of that, the derivation of the expected value here. And then the only thing is that then how much kind of the noise that we need to add, right? So as we basically have some kind of add some sort of the small the Gaussian the noise into the underlying the distribution. The thing is that we're gonna get some basically very high the accuracy for these core values near in the some highly the concentrated region like this. But for some kind of the regions which are basically quite far from the existing some kind of training the data points, basically these core the values in this region will be very close to zero, right? So which means that even when you train our score predictor, the value will be basically not that much kind of the accurate. And also since this score function will be very close to zero, there will be basically almost like the zero the moving force to getting closer into the highly the concentrated region, right? So that's kind of the problem. So if you start from any of like those regions here, with some kind of the particles here, it will not be really just moving that much into these regions, basically staying almost here. So that's basically will involve some kind of the loss of the iterations to getting closer to the highly the concentrated regions, and also even this course that we are basically predicting in these regions would be not that kind of accurate. So the other option is that basically we are increasing the variance in terms of basically adding some kind of the bigger the Gaussian the noise into the underlying the distribution. Then the good thing is that now we are not basically having some kind of the less regions, like having almost the zero discourse, which means that we can basically it's basically making it easier to move the particles into some kind of the highly the concentrated regions. The problem is that now when you have some kind of the bigger the Gaussian the noise, the modified the distribution will deviate more from some kind of the underlying the distribution. So which means that what we are using for this core function will not be that also the accurate this core function with respect to the kind of the some kind of ground truth the distribution here. So that basically motivates us in terms of basically decreasing the variance over time. So here the basic idea is that we are starting from some kind of the high the variance in terms of like adding some kind of the bigger the Gaussian noise in a way that from like wherever we start in terms of like the particles here, we still have some kind of the moving force in terms of like moving to the some highly the some kind of saturated regions like this. And as we have some kind of the particles that are basically getting closer into the highly concentrated regions like this, then we are decreasing the variance in terms of the now we get some kind of the more accurate discourse in these regions in a way that now we can get some kind of the more the accurate samples in the highly the concentrated regions. So that's the basic the motivation of like the annealed the Langevin the dynamics. So which means that in terms of like training our this core the predictor here, now we are basically varying the variance of the Gaussian the noise. So we are also going to basically learn the score for each of the time step t. So for the time step t, we are going to basically decrease the variance over the time. So for each of the time step, we need to learn this score function, right? So that's basically what we are going to do. And after like doing all the things, now this looks like the same, the thing we have seen for the DDPM case, right? So this is actually exactly the same thing with the noise predictor that we have seen in the DDPM case. So now you can see that this is kind of the same thing with the DDPM. So actually this is like one possible way to define the diffusion model, and this can be also kind of like one way to interpret the diffusion processes in the diffusion model. So we can see that actually the reverse process of the diffusion model is basically simulating this kind of the annealed Langevin dynamics. Basically started from some kind of the bigger the Gaussian noise, and then getting it smaller in terms of that we can basically make some better samples with the more accurate these core values. So that's the basic idea. And also, if we see some kind of the reverse process of the Langevin dynamics, actually that turns out to be the same with the fold process in the diffusion model, right? it's basically gradually increasing the variance in terms of that we are starting from the this kind of the distribution, which is close to the underlying the data distribution, and basically gradually adding some kind of the bigger the Gaussian noise in terms of that from wherever we start with the particles, we can basically move the particles getting close to the highly the concentrated regions. So that's the thing. So you can see that actually this is kind of the like one way to basically interpret each of the diffusion models and also sharing many things with the DDPM that we discussed last time. But actually, it's not exactly the same with the DDPM. Actually, one small kind of the difference with the DDPM the case is that at the DDPM, we defined the distribution in this way, right? So there was basically some kind of scaling term here. While in this specific case, with the annual Langevin dynamics, what we have seen in terms of like adding the noise was that we defined the fourth. This was basically some kind of Gaussian the convolution kind of distribution, right? In this case, like we defined the fourth process like this. So these two are not exactly the same. So you can say that like each of these is kind of like one specific way that we are defining diffusion models. While these are basically not exactly the same, but you can say that they are basically sharing lots of the ideas in terms of like how we can design some kind of generated the process in a kind of an iterative manner. Any questions on this?
For this model, how do we sample from the prior?
How do we sample from the prior? I mean, it's the matter of like how we define the prior distribution. So we can actually set any priority distribution. So typically, we're going to also start with the standard Gaussian distribution. But it does not need to be standard Gaussian distribution in this case.
But sigma t gets larger, but it doesn't become standard Gaussian.
Oh. Well, yeah, but in this case, the difference with the DDPM is that it does not need to be, so when we increase the variance to be very big, it does not need to be like matching the QXT to be exactly the same with the standard Gaussian distribution. So actually we're gonna we're gonna start from the prior distribution and then perform the Langevin dynamics to getting closer into the Gaussian blurred distribution. The thing is that this would be something that is kind of like deviated from the original distribution, right? So that's why we are basically gradually decreasing the variance. Yeah. Any other questions? One question you might have is that, so how many time steps that we need to have, right? So both for the DDPM and also this case, we are basically somehow have the notion of the time, right? Starting from the prior distribution and gradually performing the reverse process to getting into the one of the realistic data point, which means that in our implementation, basically we will need to have some kind of the discrete time steps, right? Starting from the capital T and all the way to going down to the zero, right? But as you can see here, actually the time does not need to be discretized. The whole idea actually can be defined in the continuous time step, right? Continuous time domain. So actually, so that's not something that we are going to discuss for today. But what we are going to discuss in the week after next week is more actually some kind of the deeper idea in terms of like what happens if we define all this kind of the process in the continuous time domain. But actually, it turns out to be that if we see this kind of the annealed Langevin dynamics process with the continuous time domain, you can see that this is actually the process that we are basically performing some kind of degeneration based on this like stochastic differential equation. So basically, this is the differential equation in terms of that we are having this term while basically injecting some kind of stochasticity here. And also, so as we define the fourth process in the DDPM and also in these like score-based models, in the continuous time domain, we can first define the process using the SDE like this. And the interesting thing that we're gonna also see next time is basically that once we basically define the SDE for the full process like this, then actually we can find the corresponding the SDE for the reverse process as well. And the closed form for the SDE for the reverse process is defined in this way. You can see that everything is kind of like this shared in terms of like those terms, and we are basically having this term, which is still the same, this core function, right? So when we discuss the diffusion models in the continuous time domains, we're gonna get back to seeing some kind of score the functions here and see how this like score function plays some kind of role in the generation process. And we can see that like all those kind of like DDPM and also these core based models are some kind of some specific cases that we are basically performing all the process with the time domain, the discretization. So that's the high level the idea that something getting deeper into the diffusion models, but we are not going to discuss this for today. So before we get into the continuous time domain, this is today's main topic that we are going to discuss. So if we get back to some kind of the comparisons for the generated models, so we have seen this kind of the main some kind of some properties that we want to basically satisfy with our the generated model, right? So what we have seen is that for the GAN, GAN is good in terms of making some high quality samples and also making it the generation the process to be fast. The problem is that it typically has some kind of mode collapse issue in terms of like losing some kind of the diversity, right? For the VAE, the problem was that it's basically fast and also making some kind of the diversity outputs. But in terms of the quality, the quality is really not good, right? That was the problem. So that is like why we started discuss the diffusion model, which is good in terms of like making high quality samples with some kind of the diversity. The problem was in the speed, right? So if you implement the things in the assignment 1, you're gonna see that actually as you have some kind of the time steps, as you basically increase the number of the time steps there, you're gonna get some kind of the better quality the outputs. Typically for the DDPM, you might need some like more or less like 1,000 the time steps, which means like 1,000 iterations, right? Which sounds like quite big iterations. So actually, the research of the diffusion, the models, recent researchers for the previous like 2 or 3 years were all about basically how we are going to basically accelerate this kind of degeneration the process. So actually, over the entire this semester, you're gonna see that we are now basically making some kind of model that needs to be performed like the 1,000 steps. We are going to see how this can be reduced into the 50 time steps. And next time, you're going to see how we can also even more like reduce this into the 10 step, the 5 step, 3, 2, 1 step. So basically, this is like all about like how we're going to accelerate this kind of the degeneration in the process while preserving the quality of the outputs. So that's kind of the big question. So as kind of the first step in terms of basically making it like the faster of the diffusion models, we're gonna basically discuss this idea, which is the DDIM. And here the key idea is that last time we basically defined both the forward and the reverse processes as kind of the Markovian process, which means that when we sample the xt, conditioned by the xt minus 1 and also any of some kind of the previous states, all these kind of the previous states can be ignored because we are assuming that xt is only depends on the one right before, basically xt minus 1. So that is basically our basic assumption in terms of defining the forward and the reverse processes, right? So that's kind of like basic thing. And here the question is that can you also basically make some kind of the non-Markovian the process? For that, what we are going to say is that for the forward the transition the distribution, what we did last time for the DDPM is that we first defined this, right? We first defined the forward the transition distribution, how we can sample the xt conditioned by the xt minus 1. And we defined this as kind of the Gaussian distribution. And based on that, we could derive the other things. This for the distribution, like I would call this like the jump distribution, sampling the xt directly from the x0. This was another the Gaussian distribution, right? And also this one as well. So this was the distribution that we need to match with our reverse process. Sampling the xt minus 1 conditioned by both the xt and the x0. So this was kind of the basic thing. But basically here the main question is that if we get back to the allowable function, so this is like something that we wanted to maximize here, is that what we need to do is that we need to basically have the probability distribution for all the latent variables conditioned by the x0. So basically, this is all about basically, what would be the likelihood for each of the latent variable conditioned by the realistic data point, the x0 here, right? So once we basically define this, if we decompose this into the multiple the terms here, then what we need to have was basically actually these two. We could say that this was basically all the decomposing into that. We just need to have these two distributions. So actually, this looks like the only information that we needed was actually not the transition distribution, but actually these two. So that basically gives some kind of the motivation in terms of that. What if we do not define the transition distribution, but actually directly define these two in a way that this all the default distribution can be defined based on these two. So that's kind of the main idea. So here basically we defined basically this first and derived these two based on this. But actually, if the only information that we need is only these two, the distribution, then would there be some kind of the other way around in terms of that we directly define these two and do not define this in terms of basically that we are modeling all this kind of fault the distribution, basically this one. Then this would be basically some more the general idea in terms of that. So this is really the idea in terms of how we are going to generalize the DDPM in terms of like define the fault process in a different way. So that's kind of the main thing. So what we are going to say is that now we are not going to define this. So we are going to basically define this like the fault, the distribution, sampling any latent variable from the x0 by only defining these two without defining this like both the transition distribution. So this would become like this. So for any of the intermediate, the latent variable, so if we wanted to xt previously in the DDPM, what we need to do was basically sampling iteratively, right? From the x0, you go to the x1, x2, x3, and all the way to the xt, right? So that's basically what we need to do last time. But instead of like doing this, now what we are going to do is that these two were basically something that we needed, right? And based on that, if we want to sample the xt, what we are going to do is that actually we are going to jump all the way from the x0 to the x capital T here, and then going backward. So basically, if you have the x0 and the x capital T, based on this, you can sample x capital T minus 1, right? X capital T minus 2, all the way to the xt. So that's kind of the another way. So when we basically define this and this, then if we want to sample the xt, then instead of like just going the default way, actually we can first directly jump from the x0 to the x capital T and just going the backward. So actually that's kind of the another way that we can actually define the fold process. Define the fold process like the reverse process, right? So that's kind of the idea. So this is kind of the idea in terms of making our default process as kind of the non-Markovian process, because now sampling of the xt minus 1 depends on both the even the xt and also the x0, which is like the first kind of the data point. So so in terms of that, we only want to define these two. Now we are going to basically switch our default process like this. From the x0, we first sample the x capital T and going the backward in terms of going to the xt. So that's basically some kind of changes that we are making. Then the question is that how should we define these two distributions? Obviously, there can be like lots of the ways to defining these two. But today, we are going to see some very specific the idea in terms of like, still we are directly defining these two while basically making these to be the same. So this was basically some kind of the default disjunct distribution, right? The sampling the xt directly from the x0, right? So we have seen how we can derive this from the previous default, the transition distribution in the DDPM case. So given the xt condition by the xt minus 1, we could derive this, right? But now we are going to define these two in a way to basically making this to be the same with the DDPM case. And this was basically the default the distribution that we have seen last time. So actually, you will see basically how we can basically define these two. You will need to do yourself. How can you define these two in a way to basically match these to be the same? Then before we get into like how exactly we need to define these two, the question might be is that, so what's the point? So why do we need to make this to be the same, right? You can see that this is like one of the specific cases of the latent variable, right? In the elbow case, basically, we are basically defining this. So for all the t, all the time t, we wanted to basically model this, right? And based on that, we are basically defining the elbow function. So this means that if we basically match this distribution, this means that the elbow function will be the same as well. So that's actually the most important part. So when we define these two distributions, while basically preserving this to be the same, what we can achieve is that we are making the elbow function to be the same with the DDPM case up to the scaling factor, right? Can you see the meaning of like this? What's the meaning of that we are making the elbow function to be the same? Yes, so the meaning of this is that once you train the DDPM model with the same elbow function, you can change the generation process. That's actually quite interesting the point. Have you seen such kind of the neural net that you trained like one specific way and use the model in different ways? Is there such kind of the case? I think there's no such kind of case, right? So once you train some kind of classification in network, can you use that network for the other kind of things? So this is kind of the interesting point in terms of that while you basically train a specific model using the objective function, in the generation process, you can run either the Markovian process, or you can also run the non-Markovian process to do the same generation. And we're gonna see what's the effect of that. Actually, that changes the performance of the generative model. So that's actually a very interesting point. We're gonna actually keep seeing this idea multiple times in terms of that once you pre-train a model, we only change the inference process, the generation process, in terms of basically improving the performance. So that's actually quite interesting, the idea. Have you seen such kind of the case? Like you train the classification network and do something at the inference time and just improve the performance. You can do this with the diffusion models without using any other information or any other kind of neural network or any other kind of some prior information, only by just changing the generation process. So that's the kind of the key thing. And this is kind of the start to see that we are making some kind of the changes in the generation process in terms of like accelerating the generation. And then we're going to actually see many other cases, like reducing the time step from the 1000 to the 50 for now, and reducing this to the 10, 5, 3, 2, 1. So that's the kind of the case. Okay, so this is kind of our main task for today, which means that there will be some quiz here. So what we want to do is that we basically want to define these two distributions in a way to basically match this, right? For all time step t. So this was basically the fold distribution that we have seen in the DDPM case. For the all time step t, we want to basically match this by defining these two, right? So it basically means that for the capital T here, this is like what we are defining here, right? For the capital T here, this should be obviously the same with this, right? By setting the capital T in the time step, right? So it's very obvious, right? So for this, we know how we need to define this, right? The problem is like this one, right? How should we define this? So, so as we already have some kind of some past experience in terms of like defining those things, you can now feel like, basically we don't know exactly, but somehow this should be something like the Gaussian distribution, right? That's what we have seen all the way from the lectures. Like all the kind of things that we are defining in the process was just the Gaussian distribution. So we can feel like it should be something like the Gaussian distribution. And for many of the cases that we have seen, actually this like mean function was also defined as some kind of linear function of those kind of the conditions, right? So while we don't have the clear idea for now, let's see that actually, let's assume that this should be some kind of the Gaussian distribution with some kind of the linear function combining these two the conditions. And then the problem would be basically finding these two. So what should be basically this like W0 and the WT? And this is actually what you need to do. Actually, this is quite doable, so very simple. So we're gonna basically consider some kind of induction. We are starting from the capital T here. We already defined this conditional distribution with the capital T to be the same with this distribution, right? Starting from the capital T, and we're gonna do some kind of induction by decreasing the time step. So let's assume that the time step t, we already basically defined the other distributions in a way that this to be the same with this. So we would like to define the other distributions in a way that basically defining this like W and the WT in a way that now for the t minus 1, also this basically holds. That's basically what we want to do, right? So which means that, so let's see, how can we derive this distribution from the qxt and the x0 for this distribution and also the other distribution that we are going to define. So given these two, this is like what we are going to define, right? And let's say like we already have this distribution. From these two, just simply by just taking this, the product like, so for this is quite obvious, right? So if you ignore the x0 here, ignore the x0 for now, then you can see that this multiplication like these two becomes the joint distribution, and taking the integral becomes just like simply the marginalization. So from the simple kind of the math, we can say that this should hold. So which means that from these to the distribution, now we can compute the xt minus 1 conditioned by the x0, right? This is obvious. And also one more thing that we actually have seen last time was this. Without proof, because some details here. But when you basically have some kind of the prior distribution and the likelihood distribution that are both of them are defined as kind of the Gaussian distribution like this, we have seen that actually the marginal distribution also becomes something like this, another Gaussian distribution. So based on these facts, now we can derive the W0 and the WT there. So once again, when you consider this as kind of the prior and the likelihood the distribution, when these two are basically the Gaussian distribution by taking the condition, the mean as some linear function of the conditions, we can derive the marginal distribution as another the Gaussian distribution, right? So then the question is that we know the prior and the marginal here. Now we want to define the likelihood, especially while assuming that this mean function is the linear combination like these two, in a way to basically simply finding the coefficients. Make sense? So let's try this. So the first thing that you need to do would be is that, so what would be the mean and the variance of this conditional distribution with respect to the W0 and the WT? And based on that, can you also derive the W0 and the WT? So this is the quiz. So yeah, if you solve those things, I think you should have this, right? For the xt minus 1 condition by the x0, the mean and the variance should be computed like this, right? So based on that, you basically derive the W0 and the WT. Then you will see that the WT and the W0 are derived in this form. Is this something that you got? Yeah. Looks quite dirty, right? But basically, but this basically shows that now we can have some kind of some kind of closed form into also the Gaussian distribution, defining this distribution xt minus 1 conditioned by both the xt and the x0 in a way that we can basically match the fold distribution to be the same with the DDPMD case. Why do we need to consider? Sorry, what was the question? Why we didn't consider some shift?
There, the assumptions function. Generally, we have to serve.
You mean some kind of some bias term here, right? Yeah. Actually, my original version of the slides is basically having the bias term there. After all the derivation, you're gonna see that actually the bias term becomes 0. But yeah. So I just basically simplify this question, that you can easily see like what we get. But typically, when we have this kind of the linear function without the kind of some bias term, we can see this kind of some kind of composition of the Gaussian that becomes another the Gaussian. So yeah. So I just like made this kind of the question simple in a way that I just already gave you this form. This distribution should be in this form. So let's also finding the coefficients. But that actually involves some kind of the intuition, like in terms of what this would look like when you define have the default distribution in that way. So based on this, so this is basically the distribution that we are defining. And also, this was the distribution that we need to match with the learned the reverse the transition the distribution, right? Here the thing is that now we don't need to specify this. So for any arbitrary variance here, so actually this is really the key point. Whatever the variance that you have here, for any of the variance term here, whatever you have, this definition of like the distribution will match the the distribution of the DDPM. So which means that there is like not just like only one way to make the non-Markovian the process. Depending on like what we choose here, even we can basically make some kind of some variations of the non-Markovian process. So we are basically saying that some kind of like very different ways to define the fold process, and also that will change the reverse process, right? The thing is that even when you make some like all the changes for the fold and reverse the processes, these are all the cases where the elbow function becomes the same, which means that even when you change our default and reverse the processes, our the objective function becomes the same. So for the same model that we trained with the same objective function, we can just change the reverse the process. So that's really the key idea in the diffusion models. So again, in the DDPM case, we defined this fold transition distribution into the specific Gaussian form in a way that we can derive like these two the distributions, right? Now in the DDIM, we are directly defining these two distributions. Then what would be the fold transition distribution in this case? I mean, depending on, so what would be exactly this? So depending on how we define these two, actually even it would not be possible to derive some closed form of like this. So in terms of that, we are seeing some kind of more easy generalization, right? So we are now directly defining these two. Even these two may not give some kind of any closed form for the transition distribution, but it doesn't matter, right? Because like based on these two, we can still define the full default process, and based on that, we can also define the reverse process. So that's kind of the key idea. So since the elbow function will remain unchanged up to the scaling factor, while basically yeah, so which means that the reverse the transition distribution will be basically still be defined in a way to basically match this distribution, and we already defined this, right, with some kind of arbitrary variance. So yeah, so that's the thing. We don't need to retrain the noise predictor. Based on the pre-trained noise predictor, now we can think about how we can really perform the reverse process in the DDIM the way. So since this is still the same, like basically the reverse transition should still match the this one with some kind of the estimate of the x0 from the xt. Whatever we have the mean predictor or the clean sample predictor or the epsilon the noise predictor, what we just need to do is that with any of the predictor given the xt, we just get the compute the estimate of the x0, and based on that we basically sample based on the distribution that we have seen for this the conditional decays. So that becomes the reverse process of the DDIM decays. So again, in the DDIM decays, so this is actually what we have seen as kind of the quiz in the previous lecture. So given the noise predictor here, noise prediction, we get some kind of the prediction of the x0 given the xt, right? So based on the prediction of the x0, what we can do is that now we can compute this whole the mean function here. Looks complicated, but we can still compute, right? And based on this, that means that we have some kind of the, we know the reverse, the transition, the distribution that should be the same with this. We sample from this and then getting the xt minus 1 and repeat this. So we are making some small changes in this part, right? Slightly changing the reverse, the transition, the distribution in the DDI in the case. So like in terms of the formulation, this might look complicated, but in terms of the implementation, actually you're gonna see that this is literally like just like a couple of the lines of the changes in the PyTorch, from the DDPM to the DDIM. And the very magical thing is that when you just like change a couple of the lines in the PyTorch with the reverse process, you're gonna see some kind of the difference in the performance. Actually, very big difference. So that's actually very magical thing. And here the question is that we now have the option to choose the variance here, right? Whatever the variance that we can choose. Let me ask this question first. So what would be kind of the maximum value here? Can you really choose any variance? Obviously, the scared the term here, this should be the 0 or greater than 0, right? But can you really choose any value here? Would there be some kind of the upper bound, maximum value? Sorry? This? Yeah. Oh, that's the right answer. Actually, yeah. Thank you for the answer. So this is the hint, right? What you can see is that we have the like square root term here, right? With the variance, which means that this is giving the sense of the upper bound, right? So basically the variance, the term, this should be same or the smaller than this, right? So we are seeing the upper bound. What's the lower bound? We can set 0, right? What happens if we set 0 in this case? So then actually, as we have seen in the previous slide, we are basically sampling the xt minus 1 iteratively from this distribution. But if the variance becomes 0, then we always take this mean as the xt minus 1. Actually, this is like very interesting case because like what we have discussed over the entire the previous lectures were all this stochastic process. We are basically doing some sampling, right? We are sampling the xt minus 1 from some specific distribution, which means that every time we are injecting some kind of the noise. So the sampling was basically like this, right? We are having some Gaussian noise here and then basically adding like this, right? So actually all the process that we have seen was basically injecting some kind of some noise, having some kind of a stochasticity, which means that even when you start from the x capital T, from the same x capital T, at the end of all the way to the generation of the process, you might get into the very different kind of the points because every time we are adding some kind of the random noise. But when you make these like variance to be 0, then the whole process becomes deterministic. So starting from some kind of some stochastic process, now actually we are discussing deterministic process, which means that if you start from the same x capital T, every time you're gonna get into the same x0 because like it's just iteration like this computation. Make sense? So this is actually very interesting point in terms of that we can find some kind of the reverse process, which is basically giving some kind of same the marginal distribution. Basically, that the output will be still the point from the same distribution, but the reverse the process becomes the generation the process becomes deterministic by setting this to be 0. So they can have some kind of lots of advantages, right? If you want to reproduce some kind of the outputs, you make some kind of images using some kind of the stable diffusion, whatever, and someone asks you to basically reproduce the images. Can you just make this image again? No, actually, because like we already have like lots of some kind of the random noise, so I don't know even how I can basically make this image again, right? With the DDIM, you can do that. If you just like remember the x capital T that you started from, based on that, if you start always from the same point, you're gonna always get this kind of the same outputs, making the generation process to be deterministic. And also you can, the thing is that DDPM is actually the special case of the DDIM. So I'm going to make this as kind of the homework. But what you can see is that if you set the variance term to be like this into quite also not very complicated kind of different form, then what you can see is that actually when you set the variance to be like this, then this becomes exactly the same with the DDPMD case. So one of the some very specific case of the DDIM actually becomes some kind of the Markovian process. So you can see that really this like DDIM is kind of like doing some kind of a generalization of the DDPM in a way that we can either increase the variance or basically decrease the variance in a way that we can even make it like deterministic. Some kind of degenerative ideas. So check out like whether this variance will really make the DDIM to be the same with the DDPM. So this is kind of the homework. And so, yeah, so typically we parameterize the variance like this in a way that 0 means the deterministic process, and the 1 means the DDPM, and you can increase this more up to that the upper bound, right? Depending on which variance that you're gonna set, you're gonna get some kind of different results, right? So why do we care about basically this like DDI in the case? So what's the meaning of that kind of the having the variance there? So it's not possible to explain the meaning of the variance like everything in this like single lecture. So we're gonna continue this discussion in the actually week after next week, especially when we go into the continuous time case. It'll be clearer like the meaning of like having the zero variance. But for now, we're gonna just see some more the empirical results, like what do you get. So we are talking about the kind of the slow speed of the diffusion models, right? So how are we going to basically reduce the time step while basically maintaining kind of quality of the outputs? So we can consider basically somehow like skipping some of the time steps. So the main thing here is that even when you basically somehow train the DDPMD model by setting some kind of the discrete time step from the 1 to the capital T, we can consider basically in the reverse process, we can consider skipping some of the time steps, having some uniform interval, not sampling from the capital T to the T minus 1, but sampling like some kind of the bunch of kind of steps, right? So even for this kind of some skipping kind of the process, actually the objective function is not being changed. So that's also kind of thing. But typically, when you basically reduce the number of the time steps, then the quality of the output also gets basically worse. But without any kind of theoretical things for now, we're gonna get into that later. The thing is that when we make our degeneration the process to be more deterministic, the thing is that even when we decrease the number of the time steps, the quality degradation is not that big, much as kind of some stochastic process. So let me show some kind of the experimental results. So this, like the image generation, the case is something that you will need to do for the image generation, the challenge. Here, basically, we use some kind of the evaluation metric, which is called the FID here. So maybe we're gonna have some chance to discuss like what this means. It's the fret insertion distance. Basically, you can see that this is kind of some sort of the distance between the distribution of the output the samples and the distribution of the ground truth, the training the data. So lower is basically to be better. And what this table basically shows is that what sort of the output that we get when we vary the stochasticity in the DDIM case, and also when we vary the number of the time steps. So when this number is basically the 1, that's the case that we are making the DDPM, right? It's saying the DDPM. When we make this to be 0, that's the deterministic DDIM case. And we can also make this to be the much greater, right? And typically for the DDPM, as I said, like we use the 1,000 of the time steps. And for the case, like for the DDPM here, this is the last rule, right? So this is the DDPM, the case. So when the time step is like 1,000, the FID is like a 4.07, quite low number. As you decrease this number of the time steps all the way to the 10 here, then you can see that the FID increases like 10 times more, like 41.07. But if you see the deterministic case here, for all the cases, basically the quality is much better. Basically, better than the DDPM case. And especially when you decrease the time step all the way to the 10 here, the quality degradation is not very big compared to this case. So this was basically the 10 times more kind of the increase of the FID, while this is like 3 times kind of the increase of the FID, right? Which basically shows that even when you basically reduce the time step in the deterministic case, now we can achieve some kind of the good results. You can compare this and this. Here in the DDPM, you needed to basically run the 1,000 time step to achieve the FID of the 4.7. Now for the DDIM, the deterministic case, only with the 50 time step, you can already get the 4.6. Make sense? So this means that what we need to do in terms of like accelerating the generation the process is not to train your model again with some kind of a new idea. Just use the pre-trained model, but just change the reverse process into the DDIM, the deterministic process, and just like reduce the time step. And then you can get some kind of the almost the same quality and also the diversity while basically reducing, speeding up the computation. So that's quite magical things, right? To accelerate the generation the process, actually you didn't need to even retrain your the model. You just need to basically change the generation the process. So that's kind of the idea. So this is actually the key things that we're gonna keep seeing in this class. So from the 1,000 to the time step of the 10, without doing any kind of fine tuning or whatever kind of things, by simply changing the generation the process, we can still match the same quality while speeding up into the all the way to the time step 10. If you want to reduce further the time steps, then now you need to have some kind of the fine tuning. So that's also the idea that we are also going to discuss. So if you see some kind of this open source model for the image generation especially, then you're gonna see that there are some kind of the options. So I guess in the first class, we also have seen the flux the case, right? For the flux, there's also kind of the model with some kind of the more the time step and also the single the time step, which is like way faster. For the single the time step, the case is the case that they somehow fine-tuned in terms of like doing some kind of acceleration. So basically, this means that if you develop some kind of the new method, that you don't even need to do some kind of like second stage training. With the single stage training, if you can make the whatever diffusion or the flow models in a way that they can run with the single step while achieving the same quality, that will be really big thing. That's kind of the unsolved problem. If you can really make some such kind of the model that is like running with the one step with the same performance, I guess you're gonna make some really big money. That's really unsolved problem. But now the state of the art is that like reducing from the 1000 to the 10, and furthermore, if you go all the way to the single step, then you need to do some kind of fine tuning. So that's kind of the idea that we're going to discuss. Question?
Oh, yeah, you know, like same quality in other domain. Worker generation.
Yeah. For the other data domain, you can use the DDIM. So actually, using the DDIM is quite standard for now, for all the cases, not only for the images, for all the other data domains. You can really use the DDIM, the ideas for all the diffusion models, not only for the image generation. And now it's not very intuitive, like why we are basically having some kind of the better quality with some kind of deterministic process. To better understand that, actually, we'll need to really get into this point in terms like how we can interpret like all this process in the continuous time the domain. So after we start to discuss like, all the things in the continuous time domain, actually what we are going to see is that DDIM is kind of the case like we are finding some corresponding ordinary differential equation from the stochastic differential equation. So it's really just like removing some stochasticity parts in the differential equation in a way to make solving the ODE, not the SDE. So we're going to basically get into this point. So what's the difference between these two? Any questions on this? So yeah, this was kind of the basic idea for the DDIM. So we discussed some kind of some basic theories for the diffusion models until this point. Next week, we're gonna get into slightly more the practical ideas. So what we really need to have in terms of the implementation to make some like images like the degenerate models, and how we can also use some kind of some pre-trained image degenerate models for some practical applications. So we're gonna have those kind of ideas the next week. Okay, I will see you next Monday.